Well, good evening everybody. It's lovely to see you all here. I'm Alan Willison. I'm the chairman of the Hertford Astronomy Group, and it's my pleasure to welcome you to this meeting. I can see quite a lot of new faces in the audience, so a very special welcome to you, and a welcome to everybody who's out there in Zoom land. I hope you're receiving me loud and clear, and you're going to have a lovely evening too. The usual little housekeeping rules just to go through at the beginning. We're not expecting to practice the fire alarm, so if it does go off, please exit through the doors each side and gather on the car park, and we will check everybody is safe and sound. If you need the toilets, they're just outside the door there. Gents up this end, ladies a little bit further along. And could I ask everybody in the audience, if you've got any electronic devices which may go off, make a noise, could you deal with them now so they don't interrupt the meeting? For those of you on Zoom, the only thing to ask you is just be careful about where you put your hands. If you touch the space bar, you may inadvertently join the meeting. For those of you who are new here, please make sure before the end of the meeting or at the end of the meeting you come along and say hello to one of the committee members. We like to make you feel welcome. Committee members are the people wearing the yellow and black lanyards, so make sure you say hello to us, because we, as I said, like to be friendly about things. So the format of the evening: in a few moments' time, committee member Martin will give you a talk about the night sky, and I'm sure he's going to show us some lovely images taken by our astrophotography group. Following that, we will have our guest speaker Simon Foster, who's going to talk about the living sun. There will be opportunities to ask questions, and could I ask if you wait to the end of the talks to ask the questions, for two reasons. The first one is the speaker might be about to answer the question you're going to ask, and secondly, sometimes it can sort of throw you out of sequence if somebody interrupts. So at the end of the talks, we'll be able to bring the microphone over to you, and that's important so that the people on Zoom will be able to hear the questions as well. And those of you on Zoom, you can send your questions in through the chat facility. We expect to finish round about 9:30, 9:45. So that's the format of the evening. So can I ask you please to give a very warm welcome to Martin Weston, who's going to talk about the night sky. Over to Martin.
So I don't know if any of you were watching the news. It had to be cancelled at the beginning of the month due to a fuel leak. So we're going through a new dress rehearsal, hopefully this month. So at the moment they have had to change the seals because it was leaking hydrogen during the test. So at the moment we're looking at March being a possible takeoff or practice run. This is actually Armistice 2 is the practice run for the Armistice 3, which is actually going to go which is actually going to land on the moon. Armistice 2 is just meant to circle the moon and come back. So the idea is to do a dry run. So I'll put a little route map here just to show what's been planned. So it's actually a 10-day mission to initially take off from the Earth and then do one orbit and then use the Earth's gravity to drive it off towards the moon, circle the moon and return. And then Armistice 3, when that actually mission is routine to go, we'll hopefully put the first woman on the moon. So we're looking forward to that. So February is a rare planetary alignment coming up and expected, or what they're calling the press calling the Planet Parade, on Saturday, February the 28th. So this is something which really, to see properly, you would need a pair of binoculars, because Jupiter's quite bright, and Saturn you can see with the naked eye, and Mars maybe. But some of the Neptune and Uranus are just, unless you know where they are, just not bright enough to be seen. I've just put a little note there saying that to have a chance you'll need to have an unobstructed view due west, clear skies, and about half an hour after the sun sets. I would just say that to be very careful about viewing this when the sun is up. Please do not try to attempt to view, especially with binoculars, especially Mercury and Venus that are close to the sun. Make sure the sun has gone down before you do any viewing. We don't want to anybody losing their eyesight for looking at the sun. So put a little note there. Why do planet parades happen? Well, the main reason for that is the planets are all on what we call the ecliptic, which is the path actually around the sun. So when the sun formed billions of years ago, out of the material, out of the disk of material the sun forms from, the planets formed, so they all sit almost in a flat plane around, so they appear to move in that elliptic. So it's not uncommon for planets to sit on the same line, but it makes good news. So I think use the opportunity to say something fantastic. And I'm sure some people say that if you're into astrology, that's important as well. This is astronomy. So this is an image that I, this time of year, quite often like to image when I'm doing my photography. This isn't one of my images, I wish it was. This was taken by the Lowell Observatory, but I am immensely interested in these particular nebula because they are created by what's called a Wolf-Rayet star. Now, most stars have a normal life in comparison. Stars like our sun, it's got a life of about 8 billion years. At the end of its life, it's used up all its hydrogen, and then it burns the helium, and then eventually it sheds off all the material and shrinks down to a size about the Earth, called a white dwarf, which is immensely dense. And all the material that the sun has created, hydrogen, helium, some of the other elements, more basic elements, are then shed into space, and then they can go ahead and create new stars. And nebulas quite often are the material that have been shed from stars. So this particular one, Thor's helmet, because it vaguely looks like the Norse god's helmet with the wings coming out the side. But the centre of this nebula is a Wolf-Rayet star, and it's actually the radiation from the solar winds that's pushing the material out. So this is, although the star is still alive and still going, it's actually shedding material before it ends. So stars of this size usually end in a supernova, where they explode, and all the material is pushed out through the medium. And they're so bright that we can observe supernovas in galaxies far away. They outshine the galaxy themselves. So this particular one is doesn't come very high up in the sky, but it's just about, well, if it was clear I would be imaging it now. But it's very close to Sirius, which is that bright star, and that you can see quite clearly. It's one of the brightest stars in the night sky, or the brightest star in the night sky. And you can see Orion in that top right hand corner there with Orion's belt. So there's a little bit of information about Wolf-Rayet stars there, just saying a little bit of information about the surface temperature there between 20,000 and 210,000 Kelvin, that is. So the ultra hot stars, they usually have a very short life. They burn the material in the star itself very quickly, and they usually end up as a supernova. So also, the heavier elements are produced in these stars that can't be produced in stars like our sun. So that's why we get these fantastic colourful images of the materials that have been lit up. So I'm going on to our images now. So this is Orion's Nebula, image taken by Alana. So that's been taken on a sea star, is it? Well done. Nice image. So it's nice to get some new faces, putting pictures into our astrophotography section. So I thought that was quite a good image. So object of the month was our cloud. Some of us are in a Facebook group called Cloud Magnets, and so this Ivana's on one of our astrophotographers, and she got the object of the month, beating me and Steve into a position I don't know where we were, near last I think, but never mind, it was always next month, Steve. But Steve holds the record. Here he is at the top of the chart. This is the league table of the Hubble Challenge. You can see recognise a few of our names in there. So there's over 1,000 members in this group, and for 4 Haggas members to get in the top 10 is quite an achievement, I think. So well done to you, Steve. Yay! Something for us all to aspire to. So this is one of Steve's pictures of Jupiter, which I think you took a couple of nights ago. Was that right, Steve? 3rd of January. So look nice and clear. I don't actually do planetary imaging myself, it's too difficult. I'll stick to nebula. So this is one of my nebulas. So this is one of my favourite nebulas. It's the Rosette Nebula. It's 100 light years across, and it's in the Monoceros Nebula constellation. Contains over 10,000 stars. Nebula is located 5,000 light years away from the Earth. Intense radiation from young stars actually cause the nebula to be so bright and appear here. But there's young stars being born. You can see in the centre there where the bright stars are. They're young stars, probably only a couple of million years old, which is nothing in astronomical terms. They're babies. I'll move on to the next image. So as it's Valentine's Day, on Saturday I thought put the Heart Nebula in there. So this again is in Cassiope, 7,000 light years away, and it's also a stellar nursery. As you can see, the young stars growing in the centre there. Should be pointing, but the pointer. Does that work? Too technical for me. Oh, place it the right way. Yep, so this is where the stars have been born here. I actually took a closer picture of that area, which is here, so you can see the stars being born there. That's called Merlot 15. So you can see the gases here. So these gases here are where the stars are being produced. So they're condensing and the stars are forming, and these are all young stars being born. I better move on. So this is Steve's Merlot 15, which is, he's using a slightly different colour palette to me, but it's an image that we continuously reprocess these as we get new methods of improving and bringing definition to the stars. And the dark areas you can see around there are actually dust clouds that are blocking the light. But this is where a lot of the material that generates the star birth is held. And this is one of Andromeda Galaxy that Steve's taken. There's 1 trillion stars in this galaxy, and it's our closest neighbour, reasonable size spiral galaxy. It's 2.5 million light years away, but it's actually slowly coming our way. So eventually, in a couple of billion years, it will probably merge with the Milky Way.
I'd obviously like to say a very big thank you to Martin for putting that presentation together, and to all the people who contributed towards it. I was jotting down a few names as we were going along there. Absolutely astounded by the work that goes into producing those. So thank you very much indeed, Martin, for sharing that with us, and for everybody else who took those photos, which we were able to share. We now move on to our guest speaker this evening, Simon Foster. I'm very pleased to welcome you to this meeting of the Hertford Astronomy Group to talk about the living sun. We know that the sun isn't just a big ball of fire in the sky. It's a little bit more than that. It's a very active star, and what happens from that star affects all the planets in our solar system. So, to tell us about sunspots, solar flares, all the latest phenomena, will you please give a very warm welcome to tonight's speaker, Simon Foster, the living sun.
So, I've got this, I think. So I've got that, yeah. Are you okay? Am I okay standing here? Is that okay? Right. Is it right if you put my slide? Ah, brilliant, right. Sorry about the rather, I suppose it sounds quite pretentious. Sorry, I had to come up with a title and I didn't know what to say. But obviously, with our sun, it can be considered, I see it as living, okay? Because it's constantly going through changes. It was born, it will go through its life cycle and it will die, just like us, unfortunately. And so there's many comparisons with us. Now, when we're trying to kind of understand the sun, I think, oh God, this is quite weird because you start thinking about it, and we're limited by, I think, a lot of our own time frame. Because with us, we all think 100 years is a long time. We look back through history and you might think 1,000 or 2,000 years is a long time. I did some like back of an envelope calculations. I think 100 years, so, you know, God willing, our lifetime, is about half a second for the sun. So, you know, and my old boss, Terry, was actually Schrodinger's grandson. So he's a quantum physicist. He didn't actually find out until he was 30, weirdly. It was a bit, and he always said, so he was talking about the quantum world, and he said, the problem with trying to understand the quantum world is because we didn't evolve in that world. We've evolved in here where we pick fruit off trees. To us, I'm trying to understand that world, get in there, is completely, you can look at it in the maths, but actually being there, trying to understand it in our own concept is beyond us. And it's a bit like that when trying to understand, if you're talking about billions of years, we throw these numbers out there, actually trying to think of that and the changes that go through. And now we compress it in trying to put it into our own time frames, it's so hard to try and figure out. And part of the problem with this is obviously when we look at the sun, we're trying to figure out what impacts that has for us on Earth. Okay, so for climate change, for aurora, for other things like that. And the problem is we try and look back through historical records, what we would call historical records, to try and predict the future. Now the problem is what we would consider historical records when you're looking at the time frame of the sun is seconds. If you think of, I'm making our existence rather bleak, but if you think of like a microbe on your body, does that, you might have the flu. You might go outside. Does that make sense? Something like minutes of changes. This microbe this is a usual change in your body. It's like us living next to this. What we're trying to work out is going on in thousands of years. Actually, we don't know if this is actually a continued process. We can look at other stars to try and get ideas, but again, we're only getting snapshots. So, yeah, I don't know quite what I'm trying to say here. So it's rather bleak, but I was going to say, we're trying to figure out where we are with the sun. How safe is it, basically? We live with this. We believe, for a long time, we just believed it kind of just emitted light, and that was it. It was called the solar constant for a long time, which is what I'm going to look at in a minute. So, I'm going to move on. Hopefully I've pitched this correct. This is kind of a bit of an open tour. I was told there's going to be some young people here as well, so I'm trying to give them an entrance into it. I was saying earlier, I'm actually very nervous speaking to you guys because, you know, I feel a bit of a fraud because I see these wonderful pictures you all take, and we just download and I just get numbers and graphs and stuff like this. And so, actually, I was saying earlier, my son's friend bought a telescope, asked me how I use it, and I was like, I have no idea. I'll go and ask people in the astronomy group, ask my friend Jonathan Pritchard, who's a professor. I have no idea how to use a telescope. I use the wonderfully named Alan Heavens, who's head of the astronomy group. I have no idea. So it's kind of you guys, I would say, it's called amateur astronomy, and I think that's slightly derogatory because I consider you guys far more professional than we are. We just, get these wonderful images, and this is taken from, I believe this is SOHO, Solar Heliospheric Observatory, so we have to always come up with acronyms. So have you heard of JUICE, the satellite that's going to Jupiter? I'm sure PhD students just sit around and most of their work is trying to come up with acronyms for satellites that are going to be launched actually. So where do we come from? Where does the sun come from? It was born. Okay. Now, actually, it was quite fortuitous that wonderful talk we had just before I come on. Actually, we are believed to be what's called a third generation star. Okay, our sun is a third generation star. So that means there was, we believe, at least two other stars. I wouldn't say in the vicinity because space is always moving, but there was two other stars before us, if that sort of makes sense. One exploded in a supernova. From that material, these second generation stars formed, and then from that, we believe the material left over, our star was formed. And it's from those, the first stars, really, there was only hydrogen and helium to fuel them. We'll talk about this in a sec. And actually, as it went through, these other generations, heavier elements were formed, like, in supernovas, where we get gold from, It's very cheesy, I always say this, but we're all made of stardust. Okay, every atom in your body has been through at least two stars, a big bang. When you think that, we're all linked back. What's amazing is, as well, we believe up to about 100 light years away, we share common ancestors with other stars, which is just remarkable that we believe that we've got like kind of elemental kind of connection to these other stars out there. So our star was formed from dust and gas left over. Okay, and it started to collapse in on itself, the hydrogen and helium. And as you were saying earlier, we've got the rocky planets. So much like a baby, okay, star came together, it started rubbing together, hotter and hotter, and fusion started. And then you had like the first scream. And with that was when the fusion started, and our star started, it came to life. Okay, part of the reason we've got the rocky planets close to the sun and the gaseous ones out was obviously when this scream happened, it was certain material was easier to push than others, so the rocky material, heavy material stayed closer to the sun, if that makes sense, and the lighter elements got pushed out. So that's kind of why we've got the planetary makeup we've got. So that's kind of where we came from. That was our story. About 5 billion years ago our story started, and this is where we are now. Okay. And what's interesting is actually the star, our sun, was about 30 to 40% dimmer when it first kicked off, okay, from what we could see. And what we believe is at the start there was pure hydrogen in its core, and it was fusing that. And actually, I'll talk about this in a second, as it's fused hydrogen into helium, the fuel mix has got, I suppose, polluted slightly. So because there's more and more helium in there, it's harder to generate the energy. Does that make sense to keep it going? It's not as efficient anymore, so it's having to generate more energy to keep itself from collapsing. And that means it's got brighter over those years. So over the 5 billion-ish years the sun's been around, it's actually about 30 to 40% more luminous. Now, over our lifetime, over thousands of years we hope to be here, we're probably not going to see much input into that. It isn't going to change that much. In that regard, the sun, which I will touch on in a minute, the sun does change quite a lot for us over what we call a solar cycle. But its kind of luminosity is increasing as it gets older. Now, you're familiar with this. This is called the Hertzsprung-HR diagram, Hertzsprung-Russell diagram. And now, if I was going to say some young people here, if you've got to do this in your GCSEs or A-levels, It's kind of our star is around here, okay? And what blows my mind is that you can actually use the wavelength of light from a star and our sun to work out its temperature. And it's just absolutely remarkable that you can just look at a star, look at our sun, and you can work out its surface temperature from the light. So have you all seen like Indiana Jones and James Bond, where they're kind of threatening someone and it goes from red to white? You know, as soon as it gets to white hot, you know you're in trouble. And you can see there the temperature is changing. You can tell it's got hotter because of the temperature. As you pointed out, does anyone remember Blackadder, the baby-eating Bishop of Bath and Wells? This is the same guy. And he was in Porridge as well, which I couldn't believe, sorry. But I always, so, you know, you can, temperature, we already know this, temperature indicates heat to some degree. And so I was going to say, this is just the equation here. So it's very, so simple even I can do it, okay? That we can work out, you look at the wavelength of the light coming from the sun and you can work out the temperature. And you can also, what's amazing is that actually we've got something called a radiance. And this is the amount of like energy we receive per like meter squared at the top of our atmosphere. And we've got satellites up there. And there's a few different ways we can calculate it. But what's amazing is you can work out the total power output of the sun using these really simple equations. So you know the irradiance. It's like a light bulb. You know you have a 60-watt light bulb, and if you captured all the energy given off, it'd be 60 watts. You can actually calculate, because we know the distance of the sun, you know, you can make a mesh around it, and you can actually calculate the total power output. As I say, these equations are very simple. I can do it. So, you know, it's amazing what you can do with just the light. Some very basic kind of calculations. You can do some amazing stuff, and you just find out all this amazing stuff about our sun and other stars. So I'm just going to go back to quantum physics for a second, weirdly, because it's really important to know how our sun's being powered. Okay, so we throw this term out there a lot called nuclear fusion. You may have heard of this, actually, young people in the room as well. So there's two different types of nuclear power, fission and fusion. Fission is large elements breaking apart. Fusion is smaller elements squashing together. Now, in the sun, we say it's fusing or burning hydrogen. Okay? So, you know, there's various chains. I just see this bit and this bit. So we get 4 protons going in, or hydrogen nuclei, and out pops some helium. There's obviously various stages along the way. This is the way I see it in my head, sorry. That's all I see, okay? All these other stages, but this is what I see. This is what it's called the proton-proton chain. It's super important, actually. And it's thanks to, hopefully, I shouldn't say thanks, but does anyone know who this is?
Einstein.
Yeah, I was going to say, you can just tell the eyes. Can you block it off? And you can see it, and obviously he had his, this is probably most people are kind of more familiar with. But obviously he's got his equation, E equals mc squared. And what's remarkable is that, if you think about it in layman's, the easiest way to think about it, that the helium that comes out is ever so slightly less massive. Does that make sense? Some of the mass has disappeared than the 4 protons that have gone in. And what's remarkable is that mass has been turned into energy. So, you know, in each of these reactions, 0.7%, just under 1%, just, I shouldn't say disappears, but it becomes energy. And this is happening every second. So, you know, we're losing millions of tons of hydrogen every second. But that's the equivalent, again, I'll talk about the human body, of us losing a skin cell. You know, it's insignificant in some ways for the sun. So not only is this interesting for solar physics, but obviously this is a snowflake. Now, I've got a lot of friends, and this has been coming for over a decade now. Well, it's been coming for my entire lifetime. It's been a decade away, and that's been nuclear fusion. And I've got some friends who work in this. But my friend Alex, who works in this, says that if you took the hydrogen from a snowflake, so obviously H2O, so if you electrolyzed a snowflake and you had hydrogen and oxygen, the amount of hydrogen from a snowflake would give you your entire lifetime supply of energy if you fused it. if that ever happened. Now, I've got colleagues that are actually, I think this is to do on Earth because there's so many stages, but I've got colleagues that are looking at, which blows my mind, my colleague Josh, and I still can't believe it, he's looking at lunar mining. So that's his job. So his job is to work out how you take the regolith, the dust on the moon. Actually, he's got two parts to it. One is to try and, because it's very helium-free rich, this isotope, okay, which is one of the stages. You can kind of jump ahead. If I go back, if you've got this stuff here, does that make sense? You can ignore these steps. You can jump straight to here. So the moon, sorry, I should say, has got lots of helium-free on its surface. So looking at that. The other big problem, actually talking about going back, the Ares 2 mission, is that if you ever listen to you read or listen to what Buzz Aldrin and Neil Armstrong said, that when they got back into the lunar module, they obviously took off their helmet and they could smell the moon. And it smelled kind of, they said, irony, like rusty. The big problem, and I had no idea about this, that that regolith is a lot like asbestos. It's really terrible. So the fear is, obviously, if we keep sending human beings to the moon for prolonged periods, as you've got, I do know the word and I can't pronounce it, but you get the lung condition when you've inhaled asbestos. Yeah. Sorry, my dad has to keep going for tests every now and again. That you could have a similar function of that. So his job is actually to try and actually, get this stuff off the surface of the moon. The second one is actually how you get it off the suits and equipment, because basically all your equipment gets clogged up really quickly. So again, though, it's remarkable. You go in his lab and you think, right, you're talking about lunar mining. There's going to be all this amazing equipment. And he's kind of got like he goes through this horrible wooden door that's all beaten up. You go down there and it's just full of Henry Hoovers and stuff like that. And you're thinking, wow, like you'd expect the lunar mining team, it'd just be amazing. There'd be lasers and all sorts. It's just Henry Hoovers and filters and coffee filters, and they're trying to figure out. And that's basically what it comes down to. Just trying to use what we've got ingeniously. So I suppose the thing is, how do we know that the sun is powered by hydrogen fusion? You can't go there. How do we actually know? There was periods where it was, is it powered by the souls of the damned, and stuff like that? Maybe, I don't know. I'd probably say possibly not. I don't know how much energy a soul produces, but we can use spectroscopy. Okay, so that means we can again use light. And I've got colleagues that just do this all the time. And I'm going to go back into just quantum physics for you younger people out there. You've probably grown. You'll probably remember that you've seen this in your GC. Have you heard? Remember, you have to go 2882 when the electrons fill up, or you go. They say 2 because it all gets a bit messy after that. But every element has got a unique fingerprint. You're all familiar with that. So it's got a certain number of protons in the core and a certain number of electrons orbiting around it. So hydrogen, 1 proton, 1 neutron, 1 proton, 1 electron. Helium, 2 and 2, lithium, and so on. Okay. Now, actually, I don't think we've got speakers for this, but I actually didn't know until recently, and I was talking to, again, Terry, who's a quantum physicist, and I didn't realise the reason these electrons actually are in these shells. I thought it was just not being a quantum physicist. I thought, it's just, things balance out and stuff like that, and I did atomic physics. It's actually because they're waves. And have you heard of constructive and destructive interference? So you can do it with sound waves. I was going to say that, you can do it where you can make actually sound disappear or seem louder. So in certain spots, it's a bit like that in that there's only certain places where waves, so this is it here. So this is constructive interference. So if you get 2 waves and you get a peak and a peak at the same occurrence, you get a bigger wave. Does that make sense? So they add up. And if you get the opposite happening, it cancels out. Does that sort of make sense to everyone? What's amazing is electrons are waves. Okay, so I work at, as I say, in Imperial. We've got the weird thing. Thomson, I'm trying to remember which one it was, won the Nobel Prize. So his father won the Nobel Prize for discovering the electron was a particle. The son, who was at Imperial, discovered, got the Nobel Prize for discovering that the electron was a wave. Okay, so they kind of won it for two almost contradictory things. But the reason these set up is that it's only at these points where the waves constructively can add up that electrons can actually exist. Does that sort of make sense? Where they're like waves. Everywhere else, they deconstructively interfere with each other and just can't exist there. So it's like, I'm always learning this stuff. I couldn't believe that, and I thought, God, I should have known that really. But as I say, I did quite well at quantum, rather. I mean,
it's not really true. The Bohr model doesn't work, right?
Well, beyond hydrogen.
So this description, they're not waves, they're quantum objects. So
Yeah, it's all right. So this is how I see it, anyway. So what can happen is, though, with these electrons, as you kind of fire one of the electrons up to another shell, so if you energize it, pass electricity through it, it will go up and it will emit light at very distinct frequencies. So you don't really see these anymore. Do you remember these horrible sodium streetlights? The young people were kind of, very lucky. It's miserable, but this is sodium and it gives off orange light because that's what the light, does that make sense? Predominant frequency when you excite sodium. And the opposite happens. If you shine pure white light through a particular gas, it absorbs in those frequencies. Does that make sense? So it's got a fingerprint that we can see. And so when you look at the sun, so it emits and absorbs in those same frequencies. So when we look at the sun, instead of getting pure light out, there's actually elements in, there's lines in there. And you could do this with like quite basic equipment, actually. I should have bought some. You can make spectroscopes with like filters and DVDs. Have you ever done that? I don't know if you've done that at school. I used to be a science teacher and we used to do it. You can actually see very faintly the absorption lines in there. It's remarkable. And that's actually the elements that's inside the sun. So this is how we found out what the sun is made of without going there. So, and I would say helium, was originally, because it's a noble gas. I'm going to be very disparate. Is anyone in here a chemist? Okay, so I was going to say chemists mainly blow stuff up, which is why I quite enjoyed chemistry. But, chemists mainly blow stuff up and make the colours. Well, obviously, helium being a noble gas, it doesn't ignite. Okay, it doesn't blow up, doesn't really do anything, it doesn't react. So obviously, we may have found it, but it's like argon, it was just unknown. So we found this trace, I say we, human beings found it, and it was helium, it was the element from the sun, so it's named after Helios, so we've got helium. So this is how we actually kind of come up with, this is how we know what the sun's made of. And there's some other trace elements in there, like iron, carbon, oxygen. This is its fingerprint. What's also remarkable, you've probably come across exoplanets. So this is how, they talk about saying you might come across an Earth-like planet. And you just think, well, how do you know that? So obviously, if you get the spectra of a star, and you can see what it's made of, hopefully it's nice and simple. It's only giving hydrogen and helium. Again, how science has changed. When I was at school, I was told that you had to put in exams, even though my physics teacher said it was nonsense, that there were 9 planets in the universe. Now there are 8 planets in the solar system and thousands in our galaxy. But the way they found them at first was, it was just you would see the dimming, the light from does that make sense? You would see a star and you would see the dimming. Now, as a planet goes across it, if you know the star spectra, as the planet goes across it, hopefully whatever's in the star's atmosphere, does that make sense, will absorb some of that light, you will see the spectra. So this is how they can say if there's water there, in the atmosphere, if there's oxygen. It's remarkable, really, that we can see these planets so far away. And so all of these have got fingerprints. And this is kind of what's key, and this is part of it we've been talking about supernova earlier, is that, as you can see, this is helium here, okay? So this is what you can say goes in hydrogen. And this is the amount of energy that comes out. Does this sort of make sense? So we've got a huge amount of energy coming out, going from hydrogen to helium. But can you see, as you progress up the next steps as helium fuses, can you see you're only getting a very small amount of energy out comparable? So unfortunately, this is why stars can't really carry on going. This is where our sun can't really go, because when it starts fusing helium, the amount of energy you're getting out is incomparable. Does that make sense, to the hydrogen? So the fuel source isn't good enough. Now, some stars can do it if they're big enough. Our sun probably won't. It will probably fuse helium in the core, maybe. It'll have hydrogen in the outer part. But I remember again, rather bleakly, my iron is the pinnacle, weirdly. So everything wants to fuse towards iron. That's the most stable element. And everything heavier than iron wants to break apart to become iron. Does that sort of make sense? So rather bleakly, if the universe is infinite, I remember my astronomy teacher telling me this, that if it's infinite, eventually the universe will just become a big cloud of iron. And he ended a lecture like that, and everyone was just like, right, okay. And we were like, right, that's a rather bleak, puts existence into kind of, right, so we'll just go become iron. Right. So that's all happening away in the core. And what's remarkable is because the core is so dense, the light, these photons that are created in the core, they can take up to 1 million years to escape from the core, because they're just bouncing around. They hit something, bounce, 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 forever going. However, when they kind of get out the core, they take seconds to shoot out. So what's remarkable is some of the light, if you think about it, the light that's made could have been made 1 million years ago. You're now seeing it's taken that long to escape from inside the core. And it goes out, you've got the radiative zone where it's shooting out, and then you've got the convection zone, and that's just material, hot material, cold material bubbling away. And this is where I love, this is where, and onto the photosphere above that, and this is where, sorry, I love sunspots, which sounds very weird, sounds like a confession, but this is on the visible part of the sun, the photosphere. You get these beautiful things called sunspots, okay? And I was going to say, this is a close-up. So I didn't actually this isn't, by the way, this is superimposed by a colleague, but what I think is amazing, so I just think this looks like the sunflowers by Van Gogh. I think it's utterly beautiful, utterly beautiful. And what's amazing is so obviously my colleague put this here, that they appear in pairs, and an average size sunspot is about the size of the Earth. And that's one of them. And you can see it here, so this is material, I'm going to talk about this more, and this is it. Can you see the convection, hot material rising? This is the convection cells, so you've got the heat in the middle, and the cold cells around it, and that's just bubbling away. And on top of that, we occasionally get sunspots. And going back to my first image, they kind of occur around, can you see you've got these loops, and these are just magnetic fields, okay? So the sun's a giant magnet, and this is where you may have heard of the solar cycle. So like the Earth's magnetic field, at the start of the cycle, it's got like a nice north and south, and it looks like, you remember at school we have the iron filings, and you'd see it, and then over the course of 11 years that breaks down, and bits of the magnetic field starts popping out, okay, where me and my PhD supervisor had a lot of terms. We called this, possibly not the nicest one, a solar hernia. Okay, so we just where magnetic fields are popping out. I had one in New Zealand, it wasn't pleasant. Things popping out where they shouldn't, okay, loops popping out. And you can see here, we've got these magnetic fields, so you can't see it in the visible light, but can you imagine there would be huge magnetic fields here? Colossal magnetic field lines in these sunspots. But why do they cause sunspots? Why do you get these darkening and these strong magnetic fields? The sun's, have you ever heard of a plasma, the full state of matter? Okay, so you get solid, liquid, gas, and then you get what's called a plasma. And that's a charged gas, and it's where the gas has become so hot, you've got the positive nucleus and the electrons kind of dissociate, and you get, I hate to use the word, soup. It's like a kind of liquidy soup of charged gas. And again, I hate to go back to my electromagnetism. Can you all remember, is it your left-hand rule? Do you remember a moving charge produces a magnetic field? You remember that kind of stuff? So this is a plasma, it's a charged gas, and obviously when that interacts with magnetic fields, you're going to get a problem, because the charged gas is because it's moving, it's got a magnetic field, and then you get magnets, and then you get magnetic fields interacting with other magnetic fields. So, God, a lot of you, I rescued this from a skip at work, and it's one of the most prized possessions. So this is an old monitor, okay, so this is what a computer used to look like, kids, okay. This is just a screen, actually, I should say. This is actually a cathode ray tube. Okay, and by that, at the back of this, I have this, so I do this in my lectures, sorry, and I'm always scared it's never going to work, because it's like I've had it, as I say, I went skip diving. And these things work by firing electrons at the screen. And when they hit the screen, they give off light. Now, how you produce an image is, because you've got a moving electron, they actually have magnetic plates at the top, bottom and sides, and those magnetic plates are constantly moving, and they can shift the electrons, does that sort of make sense, into different places, producing an image. Now, I got actually one of my students to help with this. So, I used to do this with my parents' TV all the time, and they got very upset. I used to take the stereo speakers off, and I didn't know why it worked, but it just did. But this was great fun. Now, I've introduced a magnetic field where it shouldn't be. Does that make sense? The back of a speaker has got a giant magnet on it. And now it's pulling those electrons into positions where they shouldn't be. Does that make sense? It's deflecting them out of their normal position where they should be going. And so the image that should be produced is suddenly not there anymore, and hopefully in a minute it completely, if we hit the sweet spot, completely disappears. Okay, the electrons are pushed completely out. It takes a little bit of a while to actually get. I keep fearing it's never going to work again, but that's kind of what's happening in this area here. The strong magnetic field, does that make sense, is pushing the plasma out. It can't exist. You've got two magnetic fields and they're obviously deflecting like a north and a north, and you're getting cooling in this region. So in these really strong areas of strong magnetic fields, you get cooling and you get darkening. And the sunspots have been observed, well, for thousands of years. These were the first drawings. This is from China, and this is from 1128, a monk called John of Worcester. Now, what blows my mind is, can you see how detailed his image was? This is naked eye for a forest fire. Now, I'm going to try and... This is me very shoddily doing it through my camera and a welding lens. The sun, when you actually can see it, is tiny. It's remarkable. If you look at it with your naked eye, it's tiny. I cannot believe how good his eyesight must have been to be able to discern that. It's remarkable, because this was naked eye viewing. And now, obviously, we're not sure about the scale, but these sunspots must have been colossal. Now, another scientist that came along later was Galileo, and he used a telescope to project the sun onto his wall, and he would draw them. He'd put paper up and draw them. And you can get this. Now, I did this myself. Did you ever, in the corner of books, kind of do flick drawings? You flick through and you can do, pencil and stuff like that. So, hopefully this is going to work. This probably my greatest achievement ever was getting two things working side by side in PowerPoint. Is it going to work? I force this through sheer strength of will some days. Come on. Hopefully it's going to work. The one on the right is meant to. Is it going to work? Oh. Let's try it. Oh. Is it working? No. But hopefully the Galileo's ones will. So I did that. I just animated them as a flick book. And you can see them moving across the sun's surface. Now, the one on the right-hand side is meant to be solar, from a solar telescope, and it's meant to show that they're still kind of moving in the same way. But we know since, I think these were 1613 and 1614, Galileo made his drawings. So we know for about 400 years, sunspots have been behaving roughly as they do now, if that makes sense. So we've got quite a good idea. Now, have you ever been lucky enough to go to Greenwich, the Greenwich Observatory? So if you ever see this, if you go to this room down here, this is the old solar Observatory in the corner. I think it's now got like a projector and it shows the Royal Naval College opposite. But it was originally, this room was the Solar Observatory, and they would draw, have a big telescope. There's a big circular table in the centre of the room, and they would draw them. And it wasn't just there. This started in 1874, these observations. We actually made them. If there's Hurstmonceau Castle, some were made down there when it was cloudy here. They were made in India. This is called Kodaikanal Observatory. But people started to record sunspots. Now, have you ever seen something called the butterfly diagram? So this is basically what we found was, as we were observing sunspots, we found that they first appear at high latitudes. Does that make sense? They would say, you could see where they were. They would record the latitude, the site. The books are massive. I've got them out before. The books are truly clocks. The reason I got them out, sorry, I'm going slightly off on one, is that all this data was digitized. Okay, so they were in these massive books. And the British government put out, is this being recorded? Okay, well anyway, I was told this by, anyway, so the British government put out a contract to get these textbooks digitized. And it was won, I believe, by the Philippines government. And they said, we'll do it. Okay, and they did, and they come back. And there was quite a few errors in the data, and I would sit there and moan about it, and then Henry, who was next to me, was an old Oxford Don, I would sit there and mumble and swear. And that's why I had the books, because I had to cross-check. And it turns out what the Filipino government done was got their prisoners, sat them down for 12 hours a day, and they had gone through by hand and typed in all the data through these. But I felt slightly less likely to moan after that about errors in the data. I was like, right, okay. But I got it. I got these. Now, these little dots here, these are hundreds of observations. Can you imagine how long this would have taken to go through, compute? And these were computers. These were people going through, pointing these out. This would take forever to do these. Now, I was going to say, this is, I can do this in seconds on a computer. And this is the number, and you can see the concentrations. Does that make sense? And the areas and where you could do so much now with computers. This data, it's unbelievable what we can do now. But we can see now that the sunspots, it's called a butterfly diagram, because obviously it looks like butterfly wings, and you can fold it over with an ink blot. And we kind of think this has been going on for, thousands of years. And we can see also there's something called the number of sunspots, and this goes up with this 11-year solar cycle. So as the sun flips every 11 years, we get more sunspots, then less, more. There was a period here called Dalton minimum, and there was a period here just after Galileo made his observations that they disappeared for about 50 years. Now, it's a bit of an issue about did they really disappear, or did people stop looking for them because they've been like 20 years? We're not quite sure, but there was certainly a quiet period. Now, I've got a question for you all. Sunspots are dark, okay? So the surface of the sun is about 4,000 degrees. Okay, 6,000 degrees, sorry, and a sunspot is about 4,000 degrees. I was checking if you're listening. So now, if there's more sunspots, do you think the sun's going to get hotter or colder? This is a question I was asked just before when I was a student by my PhD supervisor. So you're thinking, right, there's more sunspots. That means there's more cold regions. So I was like, right, okay, well, more cold. So the sun's going to be cooler, less energetic, or however you want to put it. He said, no, the sun gets warmer. This is very counterintuitive. Okay, and that got me, and that's where my entire career started with that, and I can literally remember that. And what's interesting, in this period called the Maunder minimum, okay, now the Thames, this hasn't zoomed, come up, this is like a drawing from the time. The Thames would freeze over. Now, the Thames was different size. I've had discussions with my physicists that the flow rate was different, so ice could propagate and all that. But the Thames would freeze over. From about October to February, March. There's reports of elephants walking on it. Okay, so it must have been meters thick. Okay, so we had a mini ice age. In one of those years there was, well, we might feel like it at the moment, but there was the summer without sun, or the summer, there was no summer. It went straight from spring to autumn because it was just miserable weather. Okay, and that was to do, we believe, with this period here. But why is that? Because obviously this is like the variation in the energy we observe as a sunspot goes across. We can see that the energy does decrease as the sunspot goes across the sun's surface. So my initial idea was correct. I was right. Obviously there's a bit more going on. So I don't know, hopefully you may have seen it, little things called faculae. And that means, as Henry has passed away, but Henry Rishbeth used to sit next to me, that means little torch. Okay, now these faculae are quite hard to observe on the sun's surface. Something big and black or dark is quite easy. Does that make sense? Something a little bit brighter on something that's very bright was very hard to see. But now we can see from telescope observations that as one of these faculae go across, does that make sense? It makes us, it increases, it makes the sun a little bit brighter. Now, rough calculation is that these faculae outweigh the sunspots about 10 to 1. 10.4, I would say, that's my, but 10 to 1. So the amazing thing is that we can use these sunspot records to actually start working out what the sun's energy output was back in time. Because this is a very simple equation, again, so simple I can do it. The sun's energy output is simply the quiet sun, and I should have said we called, by the way, that bubbling away, me and my supervisor called it the tomato soup. Because it's just like tomato soup bubbling. We had all these ideas, so we just sat there and talked about. We had a little kind of language that we used, but we called that tomato soup. And that's just the sun bubbling away. Okay, so that's the convection zone, just bubbling away. On top of that, you can add the darkening effect of sunspots, and then you get the brightening effect of these faculae. Does that make sense? And from that, you can just get the sun's energy output. And this is it with a satellite observations. So we can see since about 1980, we've got the same kind of solar cycle. Does that make sense? Up and down. If anything, it's actually slightly going down. And we can use sunspot observations to actually model the sun's energy output back in time. Fairly accurately, we think. And again, this is this Maunder minimum. So actually, we haven't had much of an increase, actually, a tiniest, about 2%. But it could have had a huge impact for us on Earth. Now, another way that we can go back in time is to use, have you ever heard of cosmic rays? So there's various different ways, but you can imagine the sun is constantly giving off a wind, but you can get rays coming from outside our solar system as well. And this is, you can imagine, this is the sun's magnetic field. Okay, and just like, because they're charged particles, they're moving, they can be deflected by a magnetic field. So when the sun's very active, this is these cosmic rays trying to come in, and they get bounced out by our magnetic field, and occasionally they hit the Earth. And what's interesting is that they're kind of anti-correlated to the sun's magnetic field, sunspot number. Does that make sense? So when the sun's very active, got a very active magnetic field, fewer get through. And when the sun's quiet, the sun's magnetic field, you can imagine, is smaller, insofar more can hit the Earth. Does that sort of make sense? So we've got records of this. And and what's great is, have you ever heard of, like, they sometimes appear, you get ice core drillings. People go up to the North Pole, and they drill down, and they use it for paleontological studies, so to study the atmosphere in the past. What's actually in there, interestingly though, is a lot of radioactive isotopes. And they're created by these cosmic rays hitting the atmosphere. Does that make sense? And creating, we shouldn't say, radioactive isotopes. One of them is beryllium-10. And that's tiny, which is remarkable. It's tiny, it amazes me how people do it. In here is tiny little bubbles of gas, thousands of years ago. And we can look at those and the radioactive elements inside it and work out how many cosmic rays were hitting the Earth, and then therefore kind of work out what the sun was doing at that time. So, this is a problem. I think you have to squint. Loads of people can see lots of different cycles in here if you squint. I'm not too convinced, but a lot of people, my friends, quiver over in Yang. If you squint, you can see kind of maybe one there. Does that make sense? And there's 2,000 years. They kind of go into this quite a lot. I'm only interested in the past couple of thousand years. But this is apparently what the sun's done for the past, maybe 10,000 years. From these, I just put it in there. I shouldn't have put it in there. I'm not. I have discussions over that. But as I say, this is going up and down. And then finally, I'm just going to quickly touch on the aurora, because the other aspect these things can have is obviously these magnetic field lines. Obviously, they're like magnets. And occasionally, I see them as, they're magnets, but I see them as like rubber bands. And if you pull a rubber band too much, it can snap. Okay? So these field lines here can occasionally snap. And when they do, they fire material, plasma, out into the solar system, and some of that can hit us. Now, this obviously isn't to scale, but when they come in, can you see the magnetic field lines here? They can snap and get pushed back around the other side of the Earth. So I might have to do some interpretive dance. But they kind of break. It's like peeling an onion. They snap and then they flip round the other way. And when they reconnect on the other side, the energy that's stored can ping back down. And this is how we get the aurora. Okay, this is the aurora australis. Now, we've actually got lots of satellites in orbit. One of them is called LASCO, Large Angle, I can't remember what the S stands for, Spectrographic Coronographic Observatory or something like that. And these are actually, I hope this is going to work, or maybe it won't. I don't think he likes it. Anyway, we've got these like early warning systems. This is slightly closer to the sun and slightly ahead of our orbit. So when it hits these satellites, we know that it's going to wash over us. Does that make sense as we orbit behind it? So, have you ever heard of the Carrington storm in 1859? Very famous solar storm, okay? And what's amazing is it fired it's called a coronal mass ejection at the Earth. A big black charge of plasma, like a belch, goes out and hits the Earth. And it was hitting the Earth and it was moving our magnetic field. It was ringing like a bell. It was moving, the Earth's magnetic field was moving back and forth. Well, if you've got wires inside a moving magnetic field, what are you going to induce in that wire? A current. When this happened, the American telegram system had just started. And it actually powered itself for a couple of days. They actually unpowered it, because so much electrical current was being induced in it. Now, what the concern is now is obviously we've got a lot more electrical equipment on Earth around us, okay? So this was the one, sorry, is this going to work? Oh, it is, right. So this was the May 2024 event. And actually what's interesting, it isn't as nice as the one I was going to show you before, okay? So that's the one coming at us, okay? So it hits us and we know, right, we're in trouble, something's coming towards us. We better do something about it. And these are two other satellites. They're not UFOs, by the way. These are two other satellites sitting there. I think this is stereo A and B. And this is my friend Matt made a model of it. So this is the kind of, think of the flare is like, it's like a gun being fired. The flare is the muzzle flash. And the bullet is what we've got, this bubble of charged gas. And we're looking down from the top. Hopefully this makes sense. And you can see it washing over us. So this is modelled after the fact. But this is my house. This is a picture taken from my neighbour. This is my son's bedroom. I'm over here somewhere, sound asleep. Okay? So my colleague Bob, who's in the office opposite me, come in and went, he's a very excellent solar observer as well. He's a solar physicist, but he's got a wonderful telescope, and he lives down near Hertford. And he was like very excited. Sunspot, same region, same size as the Carrington storm. Very nice, Bob. Very nice. Right. You know, right. He's told me to stay up before, and I've done it. I didn't have kids then. I needed a night's sleep. everyone else, some other people said, oh, it's a very big storm. It's been launched off, yeah, whatever. I need sleep. So I'm over here asleep. And it's like, we're seeing Peter and Andrea are down over here, you know, bottle of wine. Aren't you staying out? No, I'm not. I need sleep. It's not going to happen. And then this is the picture that was on my phone from Peter the next morning, going, look at your house, doesn't it look nice? Oh, God. And then Mike, my supervisor, has spent, or PhD supervisor, spent about 2 years of his life in the North Pole observing. He's an aurora physicist. And he said this is the best he's ever seen. I was like, wow. So I stayed up the next night, and obviously nothing much happened. So I slept through that. I had a good night's sleep, though, so I was actually I thought, actually, I slept well. What's interesting about this one is, obviously, it was pretty. Everyone, wasn't that nice? This came very, very close to being a very serious event. So my colleague Jonathan, well, actually, he's a very good friend of mine. We did our PhDs together, and he's quite weirdly now my boss. Jonathan is on, like, the government, I don't know, not watch list, warning group, I suppose, I don't know what you would call it, advisory group. And he got a call at 2 a.m. saying, this is the data coming in, do we need to start turning things off? Do we need to shut hospitals down? Do we need to shut the power grid off? Because there have been two events previously in Quebec and Malmo where power lines have just been melted and stuff. So this is very serious. So I can't believe that we're of the age now that people, the actual government are asking us questions. I still feel I'm about 15 and I shouldn't have any responsibility. And I was like, and he just sat there and he was like, literally flipped a coin and said, I think it's going to be okay. And it was. Okay, and it was that. He was looking at it and they were like, seriously, if we turn everything off, like, not saying you're to blame, but, you know, you did tell us. And it was like, wow, thank you for the vote of confidence. So it's, okay, right, it'll be okay. Now, again, talk about, just to give you an idea, and I remember, so my other friend Andrew, who our children were at nursery together, and we would talk about this during COVID. So we would, you know, come out the nursery and we're obviously 2 meters apart, talking and just talk about stuff. And he's a cosmologist, and we were saying, wow, aren't they handling this really badly? And, you know, and this was number one on their emergency watch list, like pandemic flu, COVID, whatever. And then he just said to me, you know, wow, they're handling this so badly. What would they do with number 2 on there? On the risk register. So this is a government risk register. Number 2, I should point out, is, well, it's number 47 here. It's a catastrophic solar storm. So, and this is their kind of, which you can see, they've got some quite large windows in here. So it can be, so really it could be up here, catastrophic and quite likely. But this is number 2. So not to scare you, but just think of that solar storm, catastrophic solar storm is number 2. And weirdly, a colleague of mine, we never understood, well, actually a student of mine, he's from Trinidad, and he sent me this from his uncle's house once. And we still don't know what caused this. Aurora in Trinidad. When the Carrington storm happened, there was aurora in. Now, Henry again, who was always convinced, and you do get them, you can get aurora around before earthquakes, possibly. So we don't know, but there was nothing, but we still don't know what caused that. And I'm just going to end on this, sorry, going back to Artemis. Okay, so when we went to the moon, I say we, human beings, we actually had no real understanding of the space environment. So my colleagues now, Helen and Tim, are actually doing the space weather forecasting for the Artemis mission. So they're saying, you know, is there going to be a good window? At the time, we had no idea. I just sent people up, okay? Now, can you see, these are the missions, 7, 8, can you see these solid grey lines? These are the times in which the lunar missions either kind of went round the moon or landed on the moon. These blue lines are when coronal mass ejections, these you know, bubbles of plasma hit us that would cause large aurora, okay? And this is the bottom, this is like the radiation detected on Earth. okay, like the background radiation. I don't know if you can see here. It goes up, down slightly because some of it is from cosmic rays. Now, this green line here is your average dose of radiation on Earth. Okay, so this is what we're all getting. Do you remember in GCSE, you might have to say you get it from rocks, food, I'm trying to remember, I used to have to teach this. Some left over from the atomic bombs, all that kind of stuff, okay? This purple dose line here is what is like safe for someone who works with nuclear material. So if you work in a hospital, nuclear power station, this is considered a safe level, okay? So, as you can probably see here, this one here, and it just missed Apollo 9. It was above their annual dose in one go. Okay, so all right, good but not great. Okay, so that's all right. Then the orange one here, and these ones, this is raised cancer risks. So this is where you get hit with so much radiation, you're doubling, quadrupling, you know, really bad. Survivable, but not, you can probably tell where I'm going, but not great. And if you watch Chernobyl, the TV series, and know about that, you can see it's that kind of scenario. Now, the one that went off just before Apollo 12, okay, that's severe radiation sickness, and that's when you're very ill. You'll probably survive it, but you're incredibly ill, okay, incredibly ill. Right, so... And lastly, this one here would have been instantly fatal. So this was, sorry, it's very bleak. I should have ended on a slightly higher note, actually, you know, kind of, you know, keep it light. But this one, and at the time, it's remarkable, it just sent people up there without knowing. Now, the point now why we're doing it is obviously that with the Artemis mission, if we can see this coming in, we've got something like 24 to 48 hours warning. We can either abort the mission and bring them back inside the Earth's magnetic field, or you can alter the trajectory so you go into a really poor orbit, but you're shielded, does that make sense, behind the moon? So you're always in the moon's shadow and you stay there. Now, you're going to abort the mission, and it's a very bad orbit, but you can do that and stay there. This is one of the main reasons we haven't been to Mars yet. Because how we're going to overcome this, it's a minimum 9-month mission. And that's the really... So sorry to name drop, but I worked with Helen Sharman. So she was my hero as a kid. And it's so weird now that I work with her, and I had to, the first time I met her, I had to go, "You're my hero." We're in a very professional meeting, and she was like, "Thank you, can we talk about this later?" And I was like, yes. But it's like, oh my God, I'm sat next to her. And now I talked to her, and she said she went to a mission at NASA, and they were talking about going to Mars, and engineers being engineers just stood up and said, obviously there might be some collateral damage, which sounds very cozy. And a lot of the astronauts kind of put their hands up and went, by collateral damage, do you mean us? And they were like, yeah. And there's just nowhere. Now, obviously, all the astronauts, most people were just going, not sure about that. Not sure about that. But that's the main reason. I personally wonder if we will ever get there. Moon is easy, Mars, because of this kind of stuff, and there's not really any way of protecting it. The current, sorry, I'm going completely off on topic, but the current level of protection is, obviously you would have a heat shield to land on Mars, you'd have your water and your food, and your, put it politely, waste. All of that will be stored behind the heat shield. If a solar storm is incoming, the idea is that you turn the ship towards the storm, hide behind that shield, that contains lots of different stuff, and hope that absorbs enough of the radiation that you survive. That's the plan. So for high technology. Sorry, and on that note, I will open it up. Sorry, a slightly lighter note than instantly fatal, but I will open up. Thank you very much for listening. I've probably gone way over time. Sorry.
For a really fantastic talk. I'm sure we got some questions from the audience. If you have, put your hand up. We'll come up there with a microphone.
I enjoyed the talk very much. What sort of margin is there between a Carrington-style event and the sort of event that would start frying our satellites?
So the one that we just had nearly was at that point. It was just below. And so the problem is these things are semi-random. They go, and this is the so when we sorry I don't know if I'm going to answer your question. I sound like a politician. I'm going to go off on one. With these sunspots, the ones that hit us on Earth are actually more likely to happen at solar minimum, because it's where. Sorry, hopefully I can go back. Oh, sorry, if I can go back to my slides. Sorry. This is the problem with it. So if I go back to this butterfly diagram, where are we? Oh God, sorry, I've been taught for ages. These ones down here are more on our latitude. Does that make sense? So these ones, so there's fewer of them. Does that make sense? On our latitude. So these happen at solar minimum. There's fewer of them, but it's weirdly, there's fewer sunspots, but this is a period when it's more likely to hit us because they're on our latitude. So you've got it's a weird thing. So you've got more sunspots, more of these solar flares, but they're less likely to hit us. If you think about it, it's very rare. So it's been, 1859 was it? So it's been, 180 years, 170 years since the last one. So, but I know the one we just had was just below the threshold. Just below the threshold where we're in trouble. So, yeah, it's trying to predict them is the problem. It's like looking at tea leaves a lot of the time. Sorry, I don't know if that answers your question.
Any other questions?
Oh.
What's the future for the sun, and how will it eventually die?
Oh yeah, so I kind of had that. So, do you know? I always keep on changing, and I was changing my talk right up to about 30 seconds before I start. Obviously, it will become eventually what's called, and again, like us. So I hate to say it, it's going through its kind of spotty period at the moment. We could say in its lifetime, and then it's going to enter its red giant phase, which we all do as well. But it will go through that, and that's where obviously it runs out all the helium. There's not enough hydrogen. The helium mix in its core is too high, so its fusion stops in the core. Quite bizarrely, fusion then starts in the outer part, higher out, and because of that, it just swells. It grows massively. This will happen in about 4 billion years. So fusion happens for about another 3 billion years in the core. And it will swell, and it will actually come out to where the Earth's orbit is. So it will swallow us up. The sun will become a red giant. It will stay like that for about 3 billion years. And then it will become, like all of it, like my nan, it will become a white dwarf. Okay? It will shrink down. Okay? And it'll be very hot and very bright, but very small. Again, like my nan. Okay? So in some ways, sorry, but it's a lot like our life cycle, really. And then over there, it will cool down and die. But yeah, unfortunately, we go when the sun goes. But before that, because the sun's as I was saying, is going to increase, it will get more luminous over that period. The Earth will become uninhabitable, I think, in about 500 million years, because the sun's luminosity will get so high. So for us, we do need a plan B, not quite yet. But God knows what we'll look like in 500 million years. So it's what we'll have evolved into. But yeah, the Earth will eventually just go. It's quite Sorry, it's very miserable. Sorry, I'm awful.
Do we have any more questions?
Yeah, great talk. I believe the corona of the sun is hotter than the surface. Can you say anything about that?
Yeah, sorry, I did delete this as well, so I was going on forever because I've run through earlier and it was about 5 hours long, my talk. So the upper atmosphere, the corona, is over 1 million degrees. And that's still somewhat of a mystery. Now, it could be that what is happening is that this is very rarefied, so it's very thin. Does that make sense? So the atmosphere is very thin, but it's very hot. And what we think could be happening is these magnetic field lines on here, sorry, I don't know if I can show it again. You can see this stretches up in to the upper atmosphere. Does that make sense? And this could be transporting energy up into the atmosphere and cooling it. And where it's so thin, you've got a lot of atmosphere, because heat is basically getting, you can imagine, it's getting hit by atoms. Does that make sense? So you've got a lot of energy going into very few, relatively, amount of atmospheres. Does that make sense? So the energy going in, it gets very hot there. It could be that, it could be magnetic, what's called magnetic reconnection. And this is where these lines, these magnetic field lines, can you see some of them? Oh, is this working? Somewhere they snap together, and as they snap shut, a bit like if you have two magnets close to each other, they snap, and there's a lot of energy in there. Could be that these reconnect, and as they're snapping together, they're pumping energy. That snapping is putting energy into the atmosphere. It's still not quite well known, really, why it's still one of the mysteries. It's called micro reconnection. But that's what we believe is happening, is these magnetic is transferring the energy up. And because it's so, as I say, thin, you've got a small amount of atoms or material there, but it's got a lot of energy. But yeah, it's still somewhat of a mystery. Everyone keeps thinking they've solved it and they haven't.
Another question here.
Thanks. There's something I'd like to ask you, which concerns star colours. Because I think one thing I find intriguing is that apparently our sun belongs to a spectral group of stars which are described as being yellow, and yet I know that if you look at the sun in the sky, it actually looks like a tiny dark blue yolk in a gigantic incandescent white fried eggs.
Yeah.
And also, and another thing, of being an artist, I know that in art material shops, there's a special light bulb which is said to produce a light very much like natural sunlight, and it's a blue light bulb.
Yeah.
So I wonder how the hell what this is. What do you think about this?
I think that's it, because it actually gives out UV a lot more than a normal light will. So I think that's why it gives it feels more, because you don't see it but you can feel it.
Yeah.
So it gives out, I think, is it UVA? Okay, I'm trying to remember. B is bad, C is cancer. I think I'm trying to remember, and A is all right. But I think it gives out UVA. It gives out small amounts of UV, so it kind of, you can feel it more. Does that make sense? Rather than your eye, but I think your body can feel it more.
Yeah.
But it's like, in the night, if you're in space, it appears white more than you know. Our atmosphere, where it's white, it's blue. It scatters out the blue part, so it appears more yellowy, orange, because of Rayleigh scattering.
Right.
I don't know if that helps. So.
Thanks.
Thank you. Do you have a question?
I was just wondering, when you mentioned the sunspots and you said about the sun's surface being about 6,000 degrees and the sunspots being 4,000 degrees, I think you said when there's more sunspots it actually makes it hotter. How is that?
But that's that's because of these weirdly around it. So you get these things called, and we don't really know, if I'm being blunt. You get these things called faculae. Okay, so what kind of is happening is the energy that should be coming out here towards you is getting pushed out into another area. So it doesn't just disappear. As the material gets kind of, if you can imagine, the heat's coming up from the core, and when it hits the magnetic field, it kind of gets pushed away. Does that make sense? It hits this, and so this part here darkens, and around it starts to warm. And I find, and this is what I find amazing, is, you know, I said that if you put a mesh around it, you can add up and you can calculate the total power. The total power of the sun over the solar cycle, we believe, isn't changing. What it is the energy we receive is changing because of our viewpoint. Does that sort of make sense? So from a different, for us it looks like it's decreasing or increasing. The opposite could be happening if we view it from the poles. Because weirdly, just how you view it and how the sunlight is coming out, actually it affects, does that sort of make sense? Like your viewing angle affects the energy you receive from it. So the total power remains constant, it just changes in different directions. And one of the directions is ours.
Thanks.
If that sort of it works in my head, sorry, I can
thanks.
see it in my head.
Very interesting,
Thank you.
I'd just like to ask, is there any particular type of measurement of the sun that you think we should be taking or that you would like to do?
I think the total solar irradiance is a big one, because we do need that. A mission that's going up that you should look out for, and I can't remember it, but my colleagues are working on it. Oh, what's it called? Sorry. Is actually looking from the sun from side on.
Right.
So instead of actually seeing as it's coming towards you, we're going to actually look at it side on. So it's going to be sun, earth, and we're looking at it from this angle, and we'll be able to see the material firing off towards us. I think a polar mission, like we were just saying there, actually having something stuck. We do have satellites that flow over, but something at the North or South Pole just stuck there and viewing down, I think would be incredibly interesting, because that way we could see is if the irradiance is energy that's hitting Earth, is that different? Does that make sense to what it looks like? And then if that's the case, then the total power is the same. It's just as this decreases, us over here increases, and vice versa. So a permanent polar one. I'm trying to remember, sorry, I can't remember the name of the one my colleagues are working on. No, but it's going to be side on, but that's again for lunar missions. Okay. But they've cancelled an awful lot. NASA have sadly cancelled a lot. There was one called Helioswarm that was going to be a huge mesh. That's gone, quite a few of them. And I don't know if you know, the head of NASA, Nikki Fox, she's from Hitchin, just up the road. She's over here a lot. If you're trying to get her, she comes over a lot. But amazingly, she's from Hitchin. So yeah, there's a hotbed for solar physics up there. Quite a few have come from up there.
Thank you very much indeed. I believe we've got questions on the internet, haven't we?
Not really questions, yeah. An excellent and informative presentation. Really enjoyed it. Please pass on my virtual thanks to Dr. Foster. That was from Christine. And Marilyn Tarotza said, "Good evening. Such a pleasure to see you all. Thanks to our fantastic speaker. Also great to see such a happy evening. A special mention for engineer Roger Groombridge. Thanks so much." That was from Marilyn Tarotza. And Neil Bartlett said, "Really enjoyed this evening. Thank you, everyone. Looking forward to next month's meeting." Not really questions.
They were easy questions.
Yeah.
Well, I would obviously like to say a very big thank you to you, Simon, for such a fantastic talk there. So well illustrated, and I'm sure all of us gained an awful lot of knowledge about the sun and what it's up to. So could you please join me? A big thank you to Simon.
Thank you.
Thank you.
Thank you.
Okay, we have a few announcements. We will circulate the details, but if I flag them up now, at least you can be aware of them. First of all, 20th of February is the next Bayford Berry Open Evening, and again, it's very good to go along there, demonstrate telescopes, show our virtual reality stuff, and get people interested in the club. I guess we met a lot of you there, and very pleased to see that you came along. On the 25th of February, 2 weeks today, Haggas have got their next meeting in this building but upstairs, and they're doing galaxy imaging. It's challenging, and we've got a talk from John Hayes on Zoom, who's going to tell you all about the basics about getting the most out of your telescopes. Do remember, if you're a member of our group, you are an automatic member of Haggas, so you can come along to those talks. You don't actually have to be sort of wildly excited about taking the photos. Listening to what the photos are about is just as entertaining and expands your knowledge. So don't worry if you haven't got the latest in astro imaging equipment. If you want to learn about those bits of those images they're taking, then do come along to it. It really is good. Our next meeting here, wow, we haven't got one talk for you, we've got 3. We are opening the doors to the students of the Hertfordshire University, and we have got 3 talks. I'll give you a rough idea what they're about. Well, I'll give you the title, so I don't think I can tell you what they're about. First of all, we've got Camilla de Giusto talking about the most powerful engines of the universe and what they have to do with the formation of stars. Then we've got Angrella Muglia, who's going to be talking about what's the matter. Well, that's matter with a capital M, so I'm pretty sure you're going to make your own conclusions about that. And then we've got Anushka Shine talking about exocomets of Beta Pictoris. Now, we've heard about exoplanets, but exocomets? Wow, that's going to be really great, isn't it? Another date for your diary, the 18th of March. That's when we have got an invitation to go along to Bengio School. It's a primary school, and each year Bengio School, sometimes along with Presdale School in Ware, hold an astronomy evening. We go along, again with the telescopes and with their artificial planets in case it's cloudy, so that people can have a little look through telescopes and get that wow moment. Our observation group, well, they have been studying the weather religiously. And the clouds have just made it a bit of a nightmare so far this year. However, we are optimistic, aren't we? Yes. Oh, come on, you can be more optimistic than that. We are optimistic, aren't we? Yes. Yes, of course we are. And when they can predict a clear night, we will be meeting up at Bramfield to get our telescopes out and try and see what's in the sky. I can't give you a date for that, we just don't know. The next bit I'm going to read, because it's about these sort of new things which us old people don't understand particularly. It's just a reminder to all new members, if they would like to join our observation group, go and see Alana, and she will add you to the WhatsApp group. Alana is the lady at the back of the room. All turn round and have a little look at her. She's waving. Yay! So go and see Alana, let her know you're interested, and we'll get you signed up. And then the moment that we think the sky is going to be clear, you'll get a message and we can all gather up at Bramfield and have a bit of fun with our telescopes. Now, there's another bit. It's about social media. Now, people like me don't always understand these things, Facebook and things, so I'll read it. Just a reminder, we are on social media. I do know that because I keep getting messages about it. So if you are on Facebook or Instagram, you can follow us at Hertford Astronomy Group, all one word. Okay, so that's pretty easy. To stay up to date with meetings, events, and see lots of the group's fabulous astrophotography work. I must say that over the last 6 months or so, our presence on this social media, I just keep getting these messages through, and then I click on them and see these wonderful pictures of what the astrophotographers are up to, what other groups are doing as well. So a very big thank you to the people who are organising that for us. So that brings us to the end of tonight's meeting. I would very much like to say a big thank you to our guest speakers, Martin for giving us that great talk about the night sky, and obviously to Simon for telling us about the sun, even if we can't remember what it looks like. So let's give them all a big clap for that. Thank you. And I'd like to say another big thank you to our hard-working tech team who do miracles with the equipment, getting it out to live on Zoom and getting the recordings edited so that we can put them on YouTube so you can catch up with them there, and working with the internet, with the website, all that stuff that goes on in the background, which makes it terrific. Very big thank you to all you. Thank you. And of course to all the other committee members who are doing their bits with the admissions and membership and, well, It's a fantastic team that we're working with there. And of course, a very big thank you to you, the audience, because if you didn't come along, well, our life would be easier, but it'd be a bit pointless as well, wouldn't it? So thank you. Have a safe journey home, and we look forward to seeing you in the future. Thank you for coming.